Hello students, hello everyone, welcome to my video lecture classes of engineering, diploma and BTech. Hello everyone, I am Debashish Das, Assistant Professor of Electronics and Communication Engineering Department, Greater Kolkata College of Engineering and Management. In this video lecture or video tutorial, we are going to study different subjects of BTech and Diploma Engineering. It will be a great session for all of you, so please be with us. Digital signal processing. In this video we are going to study about the different topics of digital signal processing and its application, how digital signal processing can be applied in different field and how the different topics is present in the digital signal processing. We are going to study about this in these videos. In this session we are going to discuss about the analog to digital conversion and the reverse of it, that means from digital to analog conversions. We all know that our whole world is analog and our systems are digital. So to process this thing from analog to digital conversion and converting the digital system to analog, the several steps required. In this session we are going to cover the following topics: the analog to digital conversions, the sampling theorem, the aliasing, anti-aliasing filter, quantization, encoding and digital to analog conversion technique. So before we are going to start about our today's sessions, first we have to understand that the whole world is analog. That means here we take an example of telephonic conversations. That means a person speak in a telephone and the voice of that person is being transferred with the help of telephone network and received by the another user of the telephone, and he or she can hear the voice, and the same way she or he replied to the sender person. To understand this thing, you have to understand the voice is the key criteria or key message in this system. So the voice we are talking is continuous in nature. That means if we convert the voice with the help of microphone and we get a continuous changing in amplitude electrical signal. That means if we speak in front of a microphone and if we analyze the electrical signal of the microphone, we'll get something like this, a continuous varying analog signal. That means the signal is continuously changing with respect to time. The voltage of the signal is continuously changing with respect to time. It is the output of a microphone, and we have to process this continuous signal into digital to transmit with the help of IP network or the internet protocol network, and we have to send this signal to the receiver end. So this is a pretty example of a digital telephone systems, and the reverse process is also taking place. That means a digital signal is being converted into a analog signal to hear the voice of the sender properly. So a conversations always there to convert the analog signal to digital signal and the digital signal to analog signal, and in the meantime in the channel there is some processing of this digital signal. Now we see first, these are the two terminologies in the analog and digital domain. The analog is continuous in nature and it has infinite possible values in 2 points or 2 steps in between points. So analog is basically a continuous in nature in both time and amplitude. In case of digital, it is discretized or discretely value signal such as integers encoded in binaries, and there are several analog to digital converter are also present in this to convert the analog signal to digital signal. So first, the sampling is the fundamental state. That means we require sampling from the analog signal to make it digital. So samples are used in real world, such as our voice call in analog signal, which is to process these signals into computer we need to convert this signal to a digital. Analog signal is continuous in both time and amplitude. A digital signal is discrete in both time and amplitude. To convert a signal from continuous time to discrete time, a process is called sampling, which is used. The value of this signal is measured at certain interval of time. Each measurement is referred to as samples. We'll discuss about these samples. Here it is a signal. You can see a signal, a continuous signal. The green line, it is a green line. You can see a green line that is change continuously with respect to time. The amplitude of the signal is changing continuously with respect to time. So this is a continuous time signal, and we take some samples in certain interval, certain and equal interval, that is t. We can see a interval of t between two samples, and this interval is same for each and every side by side samples. So we take samples from this continuous signal like this. So t is the interval between the two samples. T is the time interval between the two samples. Capital T is the time interval between the two samples, and t is the time axis of these signals. We will take also another examples of it. Sampling can be done for functional varying space, time, or any other dimensions, and similar results are obtained in two or more dimensions. The sampling frequency or sampling rate, Fs, is the average number of samples obtained in 1 second. Thus Fs is 1 by t. So t is the time interval we have seen in this previous pictures, that is t is the time interval of the two samples, between the two samples, simultaneous samples, and Fs is the 1 by reciprocal of this time, capital T. So F is denoting the sampling rate or sampling frequency. A sample is a value or set of values at a point in time or space. A sampler is a symbol or a operation that extracts samples from a continuous signal. A theoretical ideal sampler produces samples equivalent to instantaneous value of continuous signals at desired points. So we'll see how the sampling is done. In this slide we show how the sampling is being done. First, obtain a signal value from the continuous signals at regular time interval Ts, which is a sampling rate, and its reciprocals, that means 1 by Ts, gives us Fs, sampling frequency. The result of this process is just as sequence of numbers. Our discrete time signal will be denoted as xn, where n is the index, and as sampling interval Ts is defined, sampling just extract the signal's value at all integer multiple of Ts such that xn equal to n into Ts. At this point, our signal is not a continuously digital because the value xn is still take an any number from a continuous range. So we use the term discrete time signal. So we can see the above statements are nothing but just say about this. It is a continuous time signals which is varying continuously with respect to time, and we take some samples from it in equal interval, that is Ts. Ts is the equal interval of two samples, and the inverse of this Ts is the sampling frequency, which is denoted as Fs, and we can take a sampled signal from a continuous time signal. It is a sampled signal, or we can say this is a discrete time signal, but we have to keep in mind this is not a digital signal, it is a continuous discrete time signal, because the amplitude of each sample is not discrete, it is a sampled value of this continuous time signal. So it is a discrete time signal, and in this way we take sample from a continuous time signal and produce a discrete time signal. So here we can see a mathematical representations of the sampling, how the sampling is being done. It is a cost function, and we can represent a mathematical denotions of the sampling, where omega is the angular frequency. So in this way we can get a mathematical representation of a sampling. Now we will discuss the sampling rate and its comparison. That means how the sampling rate provide impact on the sampling process. We will discuss about it, and we take in this example two sampling rate. One is 2240 and one is 1240, and another is 1000 samples per second. First one is 240 samples per second, and in second case it is 1000 samples per second. So we can get the sampling time, that is Ts. For the first case it is 4.166 milliseconds, and for the second case it is 1 millisecond. Here we can write a MATLAB code to plot this sampling rate for the cos signal. Here we can see a cos signal cosine function, or we can say it is a cosine function. It is continuous in time. We plot this signal and we take samples. For first case it is 240 samples per second, and for second case we take 1000 samples per second, and we will make a comparison in the coming slide with respect to this sampling rate. Now we will discuss about this continuous time, and we will get, here we can see a continuous cosine functions as we have discussed in the previous slide. It is a continuous cosine functions, and for first case we take 240 samples per second, and we can get this type of graph. It is a discrete signal. These are all discrete time signal. And for the second case, for 1000 samples per second, we can get a graph like this. It also a continuous discrete time signal. So the rate of sampling makes a very well effect in case of discrete time signal, as we can see from this graph. You can see that if the sampling rate are more, we can get a good resolution of the signal. That means the signals look like more resolute or more analogous or more similar to the continuous time signal. And if we take a less sample per second, we can get a not so much good or not well resolution of the signal. That means the resolution of signal get hampered due to less sample. So this is the important conclusion of this topic, that if we take more samples, the resolution of the signal will be more, and if we take less samples, the resolution of the signal may get hampered. So sampling theorem states that a continuous time band limited signal may be represented by its sample and can be recovered from its sample, provided that sampling frequency omega s is the sampling frequency must be greater or equal to 2 omega m. That means the maximum frequency of the signal. That means the maximum frequency presence in the signal, in the input signal. The condition is referred as the Nyquist criteria, and this condition is referred to as Nyquist criteria. So it is a very important statement for all of us, that sampling theorem is a very important statement. It states the nature of the discrete time signal. The theorem states us that the sampling frequency should be greater twice the maximum frequency presence in the input signal. Input signal can be consist of many frequencies, so for the sampling frequency, that frequency should be greater than the twice the maximum frequency presence in the input signal. It is the sampling theorem, and this theorem is very important for all the students. Now we take an animations of this sampling and the whole process. Just take an example and have a look.
Before learning about sampling theorem, let us first learn what is meant by sampling. Sampling means taking a sample or samples from a population, which gives the entire detail about the whole population. To be more precise, taking a sample of food gives us the taste of whole food. In data communication, sampling means taking sample of signal at equal intervals, which gives the entire data about the sampled signal during reconstruction. Now, let's see an application of sampling, encoding, decoding in data transmission. Consider a person sends a voice message to another person. The voice of the person is an analog signal. This analog signal is sampled at regular time interval so that it can be reconstructed to original analog signal. The digital data is encoded for security purpose and to avoid loss of data while transmission. At receiver side, the encoded signal is decoded back to the digital data. From the sampled digital data, the original audio file is reconstructed and the receiver hears the voice message. From this, we learn that sampling is used to convert the analog signal into digital signal, and we also learn that encoding and decoding plays an important role in data communication. Now, let us learn about sampling theorem in detail. Sampling theorem. A band-limited signal can be reconstructed exactly if it is sampled at a rate at least twice the maximum frequency component in it. The maximum frequency component of G of t is Fm.
So we have seen the sampling animations. Now we take a ideal sampling and its mathematical representation. So in this representation, GT is the continuous time signal, input signal. This is the input signal we provide in the sampler. Sampler is the system where the sampling is being take place. The sampler is the system where the sampling is being take place. So GT is the input signal and G omega is the Fourier transform of this GT. And delta T is the sampling frequency. That means the frequency at which the signal is being sampled. So these two signals, the continuous input signal or continuous time signal GT and the sampling frequency omega s or delta T, is being multiplied and we get the output as a discrete time signal. This is the mathematical representation. You can see here, simply multiply, and using the multiplication property of Fourier transform, we just multiply these two signal in the frequency domain. We just get the sample signal, and if we convert into a time domain, we will get the time domain discrete time signal. In this way, we can get the sampling process, or the output of the sampling is being generated with the help of mathematical representation. So in time domain, the sampling result in a continuous time signal into a discrete time signal. It is the conversion process. Sampling is the conversion process from a continuous time signal to a discrete time signal. But in frequency domain, the sampling results in multiple translations of signal spectrum. Here you can see it is a continuous time signal, and the frequency domain representation is like this. and for impulse train the frequency domain representation is continuous, and if it is the sampled output, sampled signal, the sampled signal representation looks like this. In case of frequency domain, this side is a representation in frequency domain, that is the one side is omega and another side is amplitude, and it is the time domain representation. In one case, one side is t and it is gt, or the amplitude of the signal. So it is the time domain representation, and we can see a frequency domain representation side by side, and we can get a clear understanding of the time domain and frequency domain representation of a sampling. It is a continuous input signal, it is a sampled impulse train, and it is a sampled output signal, and the representation of the frequency domain is like this. Now we'll move into the next slide. It is the reconstruction of the sample. Just we put a low pass filter in the sampled signal, and we can reconstruct our original input signal with the help of a simple low pass filter along with a amplifier. Amplifier is nothing but to gain of the signal should be amplified to our desired level. Amplifier amplifies the gain of the input signal or after reconstruction of this signal, and in this way we can reconstruct the sample signal to our original signal. So it has a great impact to convert the digital signal into an analog signal also. We'll discuss it more detail in our last portion of this session. Aliasing. Aliasing is an important topic. Before going into aliasing, we just read out the statement of it. In case of undersampling, shifted version of signal spectrum shall overlap, resulting in a spectral disorder or distortion. In such cases, signal cannot be recovered from its sample. This effect known as aliasing. To avoid this aliasing effect due to spurious frequencies, a pre-aliasing filter is applied before sampling. That means the frequency of this sampling is an important role to recover of the signal also. That means the sampling frequency of the input signal is not sufficient, the recovery process is also get hampered. That is the Nyquist criteria, that if we do not sample the signal twice the frequency presence in the signal is being disrupted or distractions or distortion may appear. We can see in this picture that it is a input continuous time signal and it is the sampled signal, and the sampling rate, you can see the sampling rate over there. The sampling rate is much higher than the Nyquist criteria. That means twice the maximum frequency presence in this input signal. So we can get a good resolution of this signal, of the input signal, and for this is the first case, and in the second case we can see it is the equal to the Nyquist criteria. that means the sampling frequency is equal to the twice the maximum frequency presence in this signal. So we, in this case, we also get a moderate resolution of the signal. But for the third cases, it is the worst case where the sampling frequency is very less than the Nyquist criteria, and for this case the signal, the resolution of the signal is changed, or there is a distortion in the signal. See, in this input signal this look like this, and for due to the less sampling, it is the distortion occur and the shape of the input signal get changed. So aliasing play a important role to avoid distortion in the input signal, or will represent the input signal in proper way like this. So the solution is the anti-aliasing filter. Anti-aliasing filter is the solution. For that, an ideal low pass filter or band limited filter, low pass filter, that it means its limit to a certain band, and it will reject the higher frequencies in the signal presence. So the distortion is not occur in the sampler or the other digital activities. So in this way we can prevent the aliasing effect with the help of anti-aliasing filter, which is nothing but a low pass filter with desired cutoff frequency. So we'll see an animation of this aliasing process. Just have a look.
Aliasing is the effect of an insufficient sampling when a signal is digitized. The effect results in a false digitized signal with a frequency lower than that of the original analog signal. The frequency of the aliased signal can be anywhere from dc up to 1/2 of the sampling frequency. According to the Nyquist theorem, the sampling frequency must be at least twice the highest frequency contained in the signal to avoid aliasing. The Nyquist criterion guarantees that there are enough sample points to properly reconstruct the signal, provided the signal is a sine wave. Clearly, if the signal is composite and contains several frequency components, the sampling frequency must be at least twice the highest frequency component. An ideal square wave is an example of such a signal. It contains infinite frequencies, theoretically making it impossible to properly digitize.
So we have seen a animation of the aliasing effects. Now to conversion process from analog to digital, there are two more steps also there. First is quantization or quantizing and encoding. Quantizing is the breaking down analog value into a sets of finite states, and encoding is the assigning a digital word number to each state and matching it to the input signal. We'll discuss one by one about it. First we'll discuss about the quantization process and what is quantization is, which is play an important role in our conversion process from analog to digital. So quantization is the process to converting the sample continuous values signals into a discrete value data. That means xt is the input signal, that means after sampling this is the sampled value, and that sampled value is being converted into a certain levels of the discrete value data. So here we can see a 8 steps it is a 3-bit representation process, and due to that, from starting from 0 level up to 7, there are 8 steps: 0, 1, 2, 3, 4, 5, 6, 7. So there are total 8 steps is there, and they are quantized steps. And in this way, we break this process into a discrete value data. We'll discuss it in our coming slide. Say n equal to 2 to the power n, the number of possible states the converter can output is n equal to 2 to the power n, where n is the number of bits in the analog to digital converter. Example, for a 3-bit analog to digital converter, there are n equal to 2 to the power 3, that means 8. Analog quantization size q equal to vmax minus vmin divided by n. This is the step size for converting from analog to digital. So if we take a system of 10 volt, that means if a system with the input signal, which input signal is changing from 0 to 10 volt, not more than 10 volt, it is a 10 volt limited system. So the each step there will be a gap of 1.25 volt. We'll discuss it in our coming slide. We'll see how this happen. So quantization, we have 0 to 10 volt signals. Separate them into sets of discrete states, which is 1.25 volt, which we have discussed in the previous slide. So each step is quantized. For 0, we take the limit of input signal. That means if the input signal range in between 0 to 1.2 volt, it is represented at state 0. If the signal voltage is between 1.25 volt to 2.5 volt, that is represented by our state 1. In this way, we discrete or quantized the input signal in certain states. And if it is the signal is in maximum full swing range, that means it is from 8.75 to 10 volt, the signal is in state 7. In this way, we break the whole input to a certain states. It is the process of quantization, and this is the very important process. We have to break the whole analog domain into a discrete domain. You can see the whole analog range from starting from 0 to 10 volt, which is the limit of this range. The whole range is divided into 8 states starting from 0 up to 7. So in this way, we quantize the whole system. After the quantization, encoding is there. We just encoding, case of encoding, here we assign the digital value or binary numbers to each stage for the computer to read. We just assign a binary numbers for each stage of output. For 0 it is 000. There are 8 states, so 3-bit representation is sufficient to represent the 8 state starting from 0 to 7, and the binary representation from 000 to 111. For 000, it is represent the state 0. For 001, it is represent state 1. For 010, it is represent state 2, and likewise it is 111 represents the state 7. You can see the output state versus the output binary equivalent number. So This is the whole process. We will just convert the analog signal to a digital one, starting from a pure analog signal. In the stage 1 you can see a continuous analog signal. It is an important process. The whole process is being described with this picture. It is a continuous analog signal. After, first we have to sample this signal. We have sampled this signal in certain intervals of time, and the time interval is called the sampling frequency, sampling time, and the frequency is called the sampling frequency. After this sampling, it is being quantized. Here we can see represent the 3 states what we have discussed. See, this is the in the range of this. We take this as a quantization level. This signal is slightly higher than this level, so it is, we just put it down in this level. Simultaneously this signal is like this, and in this way we represent the whole signal to a quantized signal. See, it is a analog continuous signal. It is a discrete time signal, and the amplitudes of this discrete time signals are not digitized or not digital, but after quantization the system or signals is being quantized and it is in state of digital form. Now this quantized level is being converted into codes. See, for the first sample, it is the first sample, it is quantized in this system, and this is a code 100, and this code is being transmitted over a transmission line. See, 100, you can see this is the first sample code is being transmitted, and it is the second sample code 110, which is, this is 110, it is the second sample code, and third is 101, that is 101. You can see the whole quantized signal is being converted into a certain code, and this code is being transmitted over the transmission line or the channel, we can say, from the source to destination. In this way we can convert the analog signal into a digital signal, and the reverse process, that means from the digital signal to the analog signal, is being discussed in our coming slide. So this, in this way we can convert the analog signal to a digital signal. It is an example how the transmission is being take place for a digital signal. Here we can generate a parallel digital signal, and the parallel digital signal is converted to a serial transmissions of data. That means with the help of this parallel to serial converter we can convert this parallel data to the serial transmission system, and in case in the receiver end we just convert the reverse process. That means from serial to parallel conversion is being take place, and we can receive this parallel data and will make this, or it send this signal to the receiver. So in case of reverse conversion process, this is the reverse conversion process. We have discussed about the how the analog signal is converted into digital system or digital signal, and how the parallel digital data is converted into a serial data with the help of parallel to digital converter. Now, and in the receiver domain we'll discuss about the how the digital signal is being converted into a analog signal, because at the end of the hearing for a telephonic conversation we have to hear the voice, not the digital signals, because the digital signals are meaningless to hear but the analog signal makes sense. So in case of conversions of the digital signals, these are the parallel digital signals and they are being converted with the help of 8-bit DAC, that means digital to analog converter, and we get a signal like this, a certain levels of signals, and this signal is being shaped with the help of this low pass filter. It is a low pass filter, a resistance followed by a capacitor. All the high frequencies are being grounded and a low frequency will be transmitted in the output. With the help of this low pass filter we'll just recover the analog signal from a digital signal. So in this way we can recover the digital signal, or will recover the analog signal from a digital signal, or it is a recovery process of a analog signal from the digital signal, or it is simple the digital to analog converter. So in the overview process we'll just recapitulate or discuss the whole process, how the analog signal is being transmitted. Say for a voice telephony system, it is the analog signal produced by the microphone, and this signal is first sampled. It is the sample and hold circuit. S means sample, each for hold, sample and hold circuit. Sample or hold circuit produce the sample output of the signal, and they are being quantized, and with the help of ADC they are encoded into a certain codes, and these codes are being transmitted over the channel, and these binary number systems or binary digital data are being collected at the receiver end, and we convert the digital signal to a analog with the help of digital to analog converter, and at the end a low pass filter is being used to get the proper shape of the analog signal from a digital signal. You can get a discrete digital output, and with the help of this low pass filter we can get a clear shape of a analog output, which is being fed to a speaker, and with the help of the speaker we can get the analog voice output of the telephone. In this way we can convert the whole process from analog to digital and digital to analog conversions. So at the end I would like to say that the analog and digital both are important, because the whole world is analog and we have to process this analog to a digital for our transmission process and data corrections, error corrections. They are very much easy for the digital system. So digital system also required, and along with analog system. So both are side by side systems, and we have to take care of both to get a proper communication or proper processing of the system. So that's all for today. Thank you for watching. If you have any queries, you can contact to me. The contact number is given. The same number can be used as WhatsApp number. If you have any queries or doubt, you can call me or WhatsApp me to this number. Thank you very much.